Hi, this is Bert de Vries, and this is the Bayesian Machine Learning and Information Processing class. Today we're going to be talking about vector graphs. Vector graphs are a graphical method for automating Bayesian inference. It's not a mainstream machine learning method, but I think it's a very beautiful and elegant way of how to look at Bayesian inference, and so I want to talk about it in this class. What you want to do is first look at this video, then go through the lecture notes yourself. I'm going through the lecture notes, or at least sort of a guide through the lecture notes in this video. Go through the lecture notes yourself, and I also want you to read Luliger's paper here, the vector graph approach to model-based signal processing, just the first 5-6 pages. Right? It's a big paper. It's really about the idea of vector graphs and what we can do with it. There's a nice video on YouTube, probably about an hour or a bit more. Also really worth it if you're really interested. And that should be enough to get a good feeling about what vector graphs can do. So let's review. Let's review what Bayesian inference is. Let's say I have a model P of 5 variables, x1 through x5, and I'm interested in this inference task, the probability for x2 given x3. As before, we can compute this with sum and product rules. For instance, according to the product rule, this is P of x2, x3 divided by x3. And according to the sum rule, I can compute Px2, x3 by taking the original joint probability distribution over all my variables and marginalization, and use marginalization. So integrating out all the variables that I'm not interested in this case, x1, x4, x5. And I can do the same thing for the denominator. I'm just interested here in the probability distribution over x3. So I take my joint over all variables and I integrate over x1, x2, x4, and x5. And when I do that, I get the result that I'm interested in, the probability distribution over x2, assuming that I know the value for x3. Now that's this kind of recipe always works, but as you can see, that can be a very high dimensional integral. And so this can be an extremely elaborate computation. And if these would be variables defined on a discrete alphabet, I get sums of sums of sums and so forth, and the number of terms would also pretty quickly explode. So that is a big problem in Bayesian inference. And so what we do as engineers, we build models that have certain simplifications. We don't want to actually have a model, usually probability distribution over all our variables, and allow every variable to depend on every other variable. So what we do usually is build factorized models. So this is an example of a factorized model. What if P of x1 through x5 really is just a multiplication of some smaller models, a probability distribution over x1 times a probability distribution over x2 and x3, and this function now basically allows to encode all the dependencies between x2 and x3, but the assumption is that x1 is independent of x2 and x3. x2 can be dependent on x3, but x1 is not dependent on x3. And so on, px4 and px5 given x4. So by encoding a joint distribution as a product of, let's say, probability distributions that have only each one of these distributions have only a subset of variables, we are encoding an independent structure in this model, and that should really narrow down the number of computations. For instance, if I now fill in this factorized structure in as the joint here, then, well, I need to integrate over dx1, but x1 is only in this term, and the integration of px1 over dx1 is just 1, so it falls away. And in the end, this is all I need to compute. That means I can do basically I can compute this conditional by only looking at this smaller factor px2 x3 and integrate, and having a one-dimensional integral over x2 is really all I need to do. So by imposing these factorization constraints, we can really cut down the number of computations. What factor graphs essentially do is, if you have this kind of a factorized model, then doing inference in a factor graph, it automatically takes advantage of these independent structures. And it does so by passing messages between nodes that are dependent, or variables that are dependent, and not passing any messages, not any direct messages between variables that have no dependency. And so we'll see that now. We're going to work that out. Visually, or the definition or the specific, how do we come up with a graph? Well, if I have here a function, here is function f of 5 variables, and assume that is broken down into these 3 functions, right? fa of x1, x2, x3 times xb, x3, x4, x5 times fc, x4. We can represent it like this. And how do we represent it like this? Each factor, each function gets a node. Each variable, x1, x2, x3, gets an edge. And an edge is connected to a node if the corresponding variable is an argument in the function of that node. So in other words, fa is a function of x1, x2, x3, and therefore fa connects to the edges x1, x2, x3. And fb is a function of x3, x4, x5, and therefore fb connects to x3, x4, x5, and so forth. So all this representation, this graphical representation does is it's a reflection of the factorization of the joint model, if you will. Now, is that always possible for any kind of factorization? Well, there is one kind of technical detail here. What if a variable appears 3 or more times in, let's say, in 3 or more factors? That's a problem because an edge has only 2 endpoints. I cannot connect an edge to 3 nodes, right? This edge here for x5 is only connected to 1 node, x4 to 2 nodes, but I cannot connect an edge to 3 nodes. So what we do is we kind of, there's a trick around this. And the trick is as follows. Here's again this function, right? But now I have in fa is a function of x2, fb is a function of x2, and fc is also a function of x2. What do I do with x2? Well, what we do is we construct a new function g, and it is composed of the same subfunctions fa, fb, fc, but now rather than x here I still have x2 in fa, but in fb I say, well, it's a function of an auxiliary variable x2 prime, and fc is a function of an auxiliary variable x2 double prime. And how are x2 and x2 double prime and x1 related? Well, I make a new node for that, and this node says by construction f equality of x2, x2 prime, x2 double prime is delta x2 minus x2 prime times delta x2 minus x2 delta prime. Basically, this says the values of x2 and x2 prime and x2 delta prime are the same, or at least the beliefs over these over these three variables. I can draw this graph, the graph for G. So here's FA. FA is a function of x1 and x2. FB is a function of x2 prime and x3. X3 should be under here. I'm sorry. I will fix that in the lecture notes before you get to look at it. FC is a function of x2 double prime and x4. And so forth. And this node here is the equality node. That's just a function of x2, x2 prime, and x2 double prime. With this trick of introducing these equality nodes and some auxiliary variables, we can indeed make a graph for every kind of combination of, let's say, factors and distribution of variables over these factors. Even if a variable appears in 5 different factors, we just have to add a couple of equality nodes, and then we can build this graph. And so that's nice. And now, if we associate with these nodes probability distributions, then basically we can represent joint probability distributions with these graphs. For instance, if I have here P, a probability distribution over x1 through x5, and it's broken down as follows: a probability distribution of x1, x2 given x3, and you can read the rest. Then this guy here, P of x1, x2 given x3, is just a function of x1, x2, and x3. So I can associate that with this node, which is connected to x1, x2, x3. The second factor is a function of x3, x5, x4. So this node represents this distribution, or I could let it represent this distribution. It's connected to x3, x4, x5, and so forth. So now this factor graph, this we call it a Forney style factor graph because that's kind of the style that we do here, represents this factorization of this joint distribution into this factorization is represented by this factor graph. So that's nice, but so far it's just a graphical method for representing a factorized structure. We haven't done anything else yet. Now assume that I want to do inference on this joint model. I'm going to create a pretty large factor graph here. I have a function here of 7 variables, and I have FA, which is a function of and a particular factorized structure, right? FA is a function of x1 times FB is a function of x2 times FC, which is a function of x1, x2, x3, and so forth. So this is a large structure. And what I'm interested in is the marginal over x3. So basically the probability distribution over x3, and what do I need to do? I need to take this big joint and integrate over all variables, x1, x2, x4, x5, x6, x7. So all variables except for x3, and what I get on the left hand side is then my marginal over x3. This is the computation I need to do, and this in general, if x2 and x1 and x2 and if they have, let's say, it could be a very large space, but we're going to take advantage of the fact that we assume this factorized structure. So in other words, we assume this this factor graph structure here. Now, if I need to, you can see that if I need to make a sum over all these variables, and I look at just FA here, well, FA only needs to be summed over x1 because it's not a function of x2, it's not a function of x3, and so forth. So FA, we can basically move to the left over all the sum signs except for x1. And in the same way, we can do that for FC and FD and so forth. So FD only needs to be summed over X4. So what we're going to get is we can rewrite this, basically the sum of products, into this product of sums. In this here, you see sums over just one or two variables. Here, two variables here. And here I have sum over 6 variables. So, and that we've done that because we have been moving basically some of these functions over the summation signs using the distributive law, basically. You can do this algebraically, but there is a visual or graphical interpretation to what we've done. If we look at these, basically these factors now, let's just look at this guy here, the guy that is called mu with a backwards arrow, mu x5 with a backwards arrow. So call this the backward message for x5. So what's actually in here? Basically, if I have multiplied ff with fg and I'm summing over x6 and x7. Now look at this green box. This green box encloses ff and fg, and I'm summing over x6 and x7, which are the enclosed variables. So what's happening is, in order to compute this function, which is a function of x5, because x5 is the only variable that I'm not integrating over, I'm not summing over, what I need to do is basically a procedure called closing the box. I draw a box and I multiply all internal nodes, f and fg in this case, and I sum or integrate over all internal variables, x6 and x7 in this case. And what's left over is basically a new function, or you could say a new factor, sort of a composite node, a composite factor, that is a function only of the variable, well, that crosses the box, that comes out of this box. So by closing this box and integrating over all the internal variables, we've created a new node, right? The green node. And I can keep doing that. By closing now this blue box, I multiply this green node, or the message that comes out of this green node, which is this guy here, times this node fd times this node fe, and I integrate all the internal variables, which are x4 and x5, because all the internal variables already have been integrated out of the green box. So there's sort of this nested structure. You start at the terminals and you work your way from the terminals basically to the edge that you want to compute your marginal for. I can do the same thing from the right hand side of the graph, and what is left over is a message from the left hand side of the graph, the red message, that basically this composite node, this red composite node, and a message from the right hand side of the graph, this blue composite node, and apparently multiplying this message from the left hand side times the message from the right hand side computes the marginal. You can interpret this message that comes out of this box as sort of the belief that the left hand side of the graph has about x3, and the blue message is the belief that what the right hand side has about this variable x3. And by multiplying, I'm basically executing Bayes' rule. I'm fusing the two sources of information from this graph about x3. Now, note that closing boxes, we can, once I close this box, it becomes a new node and it's only a function of x5. I could just not could just not draw this box, and then I just see this arrow here. And how is this arrow computed? Well, it's computed out of this arrow, and F7. And how is this blue arrow computed? It's computed out of this message from X4, the message from X5, and FE. How is the red message computed? It's computed out of the orange arrow here from X1, this incoming arrow to FC and FC. In more general terms, the update rule for any node is you multiply all incoming messages, you multiply it with the node function, and you integrate over all incoming variables. And what's left over is an outgoing message that is just a function here of the, well, basically the outgoing edge. Mu for y is computed by multiplying all the incoming messages times the node function, integrating out over all incoming variables. This is called the sum product update rule, and I can do that for each node. I can do it for the terminal nodes, but it turns out if I close the box for a terminal node, I basically get as my message, I get the node function itself. So I can compute this message, I can compute this message. A message from a half edge equals 1, and it's in the text, you will see why. And to compute the green message, I multiply this message by the node function, and execute my update rule, my sum product update rule, and I create the green message. And I'll do the same until I have basically a forward and a backward message for X3, and I multiply, and that's it. And that is if I do that, so by just passing messages, I've basically implemented this marginalization problem by this product of sums, by this, I'm taking advantage of the distributive law. So message passing from the terminals to the edge that you're interested in is implicitly a very effective method of doing inference. And that's basically it. That's the most important thing. This is called the sum product algorithm. This is how you can do inference. You can also process information, new information, data. As I discussed, you can compute, if you close the box around a terminal, and you say, okay, so I take the product of all internal nodes, which is only FA in this case, and I integrate or sum over all enclosed variables. There are no enclosed variables. This is just a function of x1, but x1 crosses the box. So this sum falls away, and if I multiply FA by nothing, I just get FA of x. So the outgoing message of a terminal node is basically the function itself. And that allows us also to add data to the graph. Because if I now have this graph here, and I say, oh, I actually observe y, I make an observation, y equals 3. What I can do is add a node now on this end here. A node with probability distribution delta y minus 3. So just a spike at y equals 3. My outgoing message will be delta, so this the Kronecker delta or the direct delta y minus 3. So it sets y to 3. And the convention is nodes that have a direct delta as a probability distribution, we just color them as small black boxes, just to indicate it's actually observed data. There isn't uncertainty there, it is hard data. But you can just glue it onto your graph. You have a new graph now that consists of the old information we had, basically your model about all your variables, plus data. So by now passing messages, if I can pass this message, for instance, and this message from FA to FB, I can process it in FB, and compute the outgoing message to F2, then I basically get the knowledge from FA and this observation. I fuse that, and both have something to say about X2, because FB is a function of X1, X2, and Y. So it's a very efficient way of integrating information and doing inference. Now, if your system breaks apart into node functions that are kind of simple, let's say they consist of Gaussians and additions and multiplications, simple things, you can try to pre-compute this message passing update rule and just put it in a table and make a toolbox. And that's what we do. At least in our group at BiasLab, we are building a toolbox for this. So if you build your graph from a subset of nodes that are part of our toolbox. Our toolbox is called Formulab, and it's simple enough. You can imagine that by just pressing a button, you get your inference answer, because Formulab will then just it will build the graph for you, and it can just compute all these messages by looking it up in the table lookup, basically, and so you automate inference. Let's apply that now to in example. We're going to do regression. We have a data set here, so here is Z and here is the response. Right, there is basically a function of Z plus some noise, so there's a noisy response. We want to find the curve here through these data points. What we do is we build a model. This is our model. We say Y is a linear function of some features of the inputs X plus noise, and we give priors on the noise and priors on the parameters. Now we can rewrite this as a factorized model. You should really think about that, that's possible. And that means if I write it as a factorized model, then I can draw the graph. This graph here is nothing but a representation of our model. And if we now observe a data set D, and D I just pairs x1, y1, x2, y2, and so forth, I can glue them onto the graph as nodes here. So here x and y, they are observed. And then I just do message passing from the terminals blah 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 till omega or w, and that should get me a posterior for w that integrates basically my model assumption, or let's say all the white boxes, plus my observed data. I also assume that sigma squared, which is a function here in a variable in my model, is observed, and x is observed and y is observed in my training data set. And the integration of all this stuff, what does it lead for my belief? What is the result in my belief for a w? Well, we can do this algebraically, but we can also just push a button, encode this model, tell the model where the data is, and just push the button. And by message passing, you will get an answer. That's what we can do in this code. You can read this code. We will also we can talk about it later if there are still questions about it. What will happen is we build our vector graph by basically saying that well, x is a variable, d by this or y is w times x. Well, basically this just builds the model, and we build placeholders for where the data is. Say now make some product algorithm. Here's the data, and just execute the subproduct algorithm, and that's it. And then you plot the result, and this is what you get. Here are these. You get a posterior for w, and if we just draw a sample out of that posterior and draw the curve, and we do that again, draw another sample out of the posterior for W and draw another curve. We get a bunch of curves, and each one of these curves is a potential solution. We didn't get the exact curve, but that's totally proper. We just have a finite amount of data, so we have remaining uncertainty about what the exact underlying curve is, and so this is all fine. And this is automated inference, and that's what you can do with vector graphs. There are some optional slides that you can read through if you want to, but generally the optional slides are not slides that are going to be on the exam. So that's vector graphs. There's of course a lot more to say about vector graphs, but I think this will be enough for this class. So read the lecture notes and read Lulica's introduction, or at least the first 5 pages or 6 pages, and you'll be fine. Bye-bye.